Rish, can you hear me?
Yes, sir. I can hear you.
Okay. Rish, did you remind the speaker this morning?
Yes, I sent a mail today around 9.
You think she replied, right?
Yeah, she replied.
Hey, Zongzi.
Hi, good morning, everyone. Hi, Prakash. Good to see you.
See you. Thank you for joining. And could we test out your slides to make sure we can see your slides, and then we can come back and introduce you?
1 second. Um, Let me just try to switch my audio up a little bit. So,
No, I can't hear you. Can you speak?
test.
Yes, it's
Yes.
yeah.
Okay, great.
We just want to test your slides first, and then we can go back to the flyer to introduce you. Can you?
Yeah.
Can you share your screen? Can you try to share your screen?
Yes. Let me try to share. Could you see the screen? Just shared.
It's coming. Oh, yes, we can. We're good. Harish, can you go back to the flyer so I can introduce the speaker?
Should I stop share?
Yeah, you can stop.
Okay.
Okay, good morning, everyone. We can get started. Now, this is a distinguished webinar series in AI and cybersecurity hosted by University of North Dakota and along with other universities as well. Today's speaker is Dr. Zhongzi Wang, Assistant Professor, Department of Electrical and Computer Engineering, Colorado State University. The title for today's talk is Transforming Grid Modernization, Advancing Optimal Dispatch for Resilient and Reliable Grids. Dr. Zhongzi Wang is an assistant professor in electrical and computer engineering and affiliated faculty member in systems engineering at CSU, where she directs the Grid Modernization Initiative at the CSU Energy Institute. She is recognized for her expertise in optimizing hybrid transmission and distribution operations, grid resilience, vegetation management, and energy policy, and serves as a lead principal investigator on projects funded by the U.S. Department of Energy, National Science Foundation, Eversource Energy National Lab, IOC, New England, and Mysore. Before joining CSU, Dr. Wang was an assistant professor in the Electrical and Computer Engineering Associate Director of the Eversource Energy Center at the University of Connecticut, leading efforts in grid modernization, workforce development, and industrial training. Prior to that, she was a postdoctoral research associate and lecturer in systems engineering at Cornell University and collaborated with Ministry of Energy in Ghana and Power Quality on grid planning. She is the general chair of the 57th IEEE North American Power Symposium, a senior member of IEEE, vice chair of IEEE Power and Energy Education Committee, Award Subcommittee, secretary for the IEEE PEC research, and an active member of several IEEE Power and Energy Society subcommittees, working closely with utilities, software vendors, independent system operators, and other institutions. Dr. Wang, it's a great honor to have you as part of the webinar series. Thank you for spending your morning with us on this webinar. The floor is yours.
Thank you very much, Prakash. That's a very informative introduction. Let me just start sharing my screen. Send request. Okay. You can see the screen, right?
Yes, be good.
All right, perfect. Good morning, or maybe good afternoon, everyone, depending on where you are. I appreciate you joining the seminar and listen to the talk. And again, thanks very much, Prakash and your team, for inviting me for the talk and for making the very good introduction. My name is Zhongji Wang, and very honored again to be invited and speak at the seminar. I'm excited today to talk with you together in a high level or in general, how we can really transform the grid modernization. How do we build a resilient and reliable grid through optimal dispatch? Well, today I'll start with a high-level background on the grid modernization and then move into some of the practical application examples. And then we have been working on these examples to highlight some of the projects. And after that, since I am coming from CSU, I'll introduce our CSU's Grid Modernization Initiative and the Energy Institute hardware facilities. Well, before we dive deeper, I really wanted to take a moment to reflect what's happening for the grid and for the energy systems in general. Globally, we see more frequent severe storms, heat waves. We see for example, the damages on the Alaska infrastructure. We see the nuclear. We see the different hydropowers, and we see the different type of extreme weather events that are having, or the other large-scale disruptions that really remind us how critical our energy systems are. So these events, from my perspective, they don't just test the reliability of the grid, and they also drive a higher energy demand and operational challenges that kind of ripple across the different territories. And this is a figure to show you that you can see this figure highlights the projected increases in the energy use across the United States. And this actually shows how our system will continue to face, for example, heavier loads in the years ahead of us, right? And this is one of the key motivations behind my work that is keep on driving my work. And this is to, for example, strengthen the reliability and resilience of our power systems as they evolve, and then also to make sure that we're really prepared for whatever challenges that comes next. I know that many of you are from power system expertise or electrical engineering background, but just wanted to show you briefly about power systems. Power systems, we have generation system, transmission system, distribution system. My research is really focused on transmission, distribution system, and coordination of the both systems. So from the transmission perspective, we have the high level voltage and transmission system usually operated either by RTO, we call regional transmission operators. For example, some of the utility companies, let's say Xcel Energy here in Colorado, is one of the typical RTOs. We also have the 7 different independent system operators we call ISOs in the United States that are operating in generation transmission systems. And one of the ISOs here that is located regionally is we call Southwest Power Pool, SPP. Well, when it comes to distribution system is relatively a low or very low voltage level. We call the distribution system that are usually managed by the utility companies, for example, Xcel Energy or Eversource Energy, Avangrid, National Grid. These are the major utility companies that are managing the distribution system at the same time. Well, the mission is actually very clear. Our mission is really to advance the reliability, resilience, energy efficiency that can really bridge the research innovations with a real world application. And behind of all of these policy drivers are also very important factors. For example, we have FERC Order 2222, 841, 2023. They're all shaping the modernization by enabling distributed participation, the grid flexibility, or streamlined interconnection process, right? And I always talk to people around that simulation or the co-optimization tool, they always form the foundation or pushing forward for the great results. And here I just listed some of the popular simulation tools, for example, OPAL-RT, that is very popular for the hardware in the loop simulation for real-time dynamic simulation. We have MATPower that does steady state power flow, and this is from the MATLAB. Of course, you can also see PandaPower from Python with a similar version of the programming. And PPOPF is something I'm very excited to share with you today. It's something that I developed when I did my postdoc at Cornell University and has been later on acknowledged and used by many other different projects and different applications. Another one is a Power Models ITD, which is ITD means Integrated Transmission Distribution. This is an open source software that has been developed by the scientists from Los Alamos National Lab by coordinating the transmission and distribution system together as a co-optimization tool. And there are other different type of the software and the hardware for the simulations that, of course, you would also be very much understanding of the others. Well, in terms of the grid impacts, I'll just quickly go over that. All of these together really help to improve the reliability, to strengthen the coordinations between the different type of the systems, and to accelerate the technology transition towards a more resilient and future-ready grid. And speaking of that, I wanted to show you a high level of the power system application. On the left, you see this technology development. It can be DER modeling and some of the machine learning technologies to focus on the grid reliability, resilience, TNT coordination, and the other different simulation tools. And then in the middle part is the optimal dispatch validation, which is essentially a very important validation that we really, as a power system engineer and scientist, we wanted to validate. So from the technology development to the optimal dispatch validation, there's so many different approaches. For example, we have the different simulation interface. How do we build the platform in between? We have the different performance-based metrics that we have to characterize. We have the different data scheduling or dispatch hierarchical information that we need. And not only that, as I mentioned from the previous slides, market or policy is always driving behind us to push it forward, right? And starting from the market perspective, how do we really integrate the different energy policies or regulation perspective to make it work? And how do we develop a decision analysis tools to also kind of enhance the situational awareness? So from the market policy to validate the optimum dispatch, again, there are also many other different approaches. I'm not going to share all of these in details, but you can see also from the slides. And this is what I wanted to talk about first, is related to the optimal dispatch validation. And that includes many different software tools that can make it work. For example, the PPOPF is as a dynamic optimization framework, which I'll share a little bit more detail. Well, in terms of the PPOPF, let me just quickly share the high-level background behind this. We are talking about a dispatch control hierarchy in the power system operation perspective. Power system operation, we have multiple different dispatch levels, right? We have day-ahead scheduling, which is 24-hour ahead. We have the real-time dispatch. We have AGC called automatic generation control. So if we do not have any of the variable energy resources in the past, if we only have the traditional loads, forecasting area is pretty matured already. It's about 2 to 3% in terms of the day ahead forecasting. Now, with a lot of variable energy resources, it can be as high as even 30 to 50% just for even for a 24-hour ahead of us. So the total forecasting area can be 32 to 50%. That just gave you a rough number of how that looks like. And that is really much larger than what we could handle from the AGC perspective. Usually in the US, we could handle the power adjustment limits about 5 to 8%. Depends on the different type of the ISOs or different territories or how much of the penetrations of the variable energy resources they have, usually around this percentage. Well, the forecasting area is so much larger, and that could really jeopardize the power system stability, reliability, as well as the security. So what do? Is we add a middle layer called real-time dispatch over here, so that a real-time dispatch, after whatever is coming out from the day ahead scheduling, the real-time dispatch can use the balancing reserves from those, for example, conventional generators to update and correct all of these different balancing or imbalance, and then to make sure that whatever is coming out of the real-time dispatch going into the AGC can be within the AGC limit. So the real-time dispatch is really playing a critical role in terms of the power balancing in the power systems. And speaking of that, the goal of doing this PPOPF is really to provide a multi-stage related to the day-ahead scheduling, real-time dispatch, AGC, and also to target a time-varying optimal power flow framework that is helpful to achieve accurate optimal generation schedules during both day-ahead scheduling and real-time dispatch with the benchmarking algorithms. So when it comes to the generation schedules, it's usually executed by the system operators based on the net load forecast, which are the traditional loads, as well as the variable energy resources. Well, this is a figure to show you the differences between the actual curve and the forecasting power output. As we can see, the actual power generation is a continuous curve with respect to time, while the power forecasts are usually predicted at the discrete time points. And in other words, it discretizes the actual power curve into a sequence of the power time points. So the output levels in between the two consecutive discrete time points are approximated by linear interpolation. So from the perspective of the continuous temporal domain, the forecasted power output is a piecewise linear function of time. And since when we're trying to make the generation schedules, right, we do not know how the actual power really look like because it's always hours or minutes ahead of us. The only thing we know is this forecasting power output that is being applied. So we use that to achieve the optimal generation schedule, such as during the day ahead and the real time. And one of the typical thing that we do is optimal power flow, right? Optimal power flow is a very useful tool, which I will share a little more in the future, later on in the next slides. So traditional optimal power flow that is being used is really focused on a single specified time point. And now we apply that solution or optimal solution to the system operational horizon. Well, since we talk about the OPF, again, how do we solve the uncertainties and enable to achieve these optimal generation schedules? It is very necessary to implement the optimal power flow as an optimization tool. And optimal power flow, just in the other words, is how do we optimize a power system to achieve an optimal objective functions that can either be minimizing the generation cost or try to minimize the congestion management while satisfying a different type of the constraints, including a quality constraint, which we usually talk about the AC or DC power flow equations, and also to satisfy a different type of the inequality constraints can be related to the voltage, thermal limits, any other dynamic control or related constraints, right? So that is an optimal power flow. And then after solving this framework, you get a solution, and we call that solution as an optimal power flow solution. So coming back, this is an example to show how the traditional optimal power flow really works. If we look at the time interval 1 between the time point A and time point B, traditional optimal power flow considers both objective function and the constraints on the beginning time point A, and then they apply the corresponding optimal results into any other time points in this time interval 1 until the time point B. Right? And specifically, think about it. There can be some of the issues. First of all, the power flow distributions at the specified time point, they may not perfectly represent the other non-specified time points for those power flow distributions. So the operational constraints that are satisfied at the specified time point, they do not guarantee the same constraints to be also satisfied at other non-specified time point, and especially if we consider about the binding constraints, or if we consider a lot of variable energy resources, then the power distribution in between the point A and point B, they could vary drastically due to the uncertainties. And this can really jeopardize the system security and stability, especially if we consider a lot of heavy over limits when it comes to the constraints violations, right? So a good optimal power flow question mark is, a good optimal power flow should be able to ensure that the constraints are satisfied at any time point within a given time period. In other words, instead of using just one single specified time point to represent the entire time period, a fundamental characteristic of the optimal power flow is to specify a set of proper discrete time points to represent the continuous time period. Well, again, the question mark is, to achieve such a goal, right? How do we select the specified time point, that minimum time points as that can better represent the entire time period? Well, to come up with such a question is to come up with such a model is very interesting, but it is also very challenging, especially when we are trying to cover all the constraints over all the time points in the entire time period, right? And given the time or the power system is a large-scale nonlinear and dynamic systems, it's just not intuitively straightforward to optimize the numerous or the high-dimensional variables in the power system with the variable energy resources. And this is an example I wanted to share with you to better explain the problem. So let's say during the day I have scheduling, as I mentioned, the first level of the dispatch control hierarchy, right? We have a time horizon of the 24-hour. Traditional optimal power flow is focused on the beginning time point during each 1 hour time interval. So to make sure the power system is being secure, the system operations on the other time points in this 1 hour interval are also considered. And more specifically, if we have an IEEE 118 bus, this is a very popular test case. I believe many of you have been working on doing the R&D work, right? If we consider this bus system, 118 bus system, then we have to make sure that under each time point in this 1 hour, the system constraints on all of these 118 buses should all be satisfied. And the constraints I listed over here are only the fundamental constraints that must be considered for system security from optimal power flow perspective. And of course, there are many other constraints, as I said earlier, for example, the control devices or any other dynamic related constraints can also be considered. And you may have noticed that even for the fundamental constraints on just one time point, the number of the variables is already a lot. And now, if we consider all the other time points in this 1 hour interval, then the sum of the numbers of the constraints will be high dimensional. And this is just an example for 118 buses. What if we have another large-scale practical power systems that has over 13,000 buses? It's going to be a dimensional curse. Well, so starting with a question, these are some of the desirable characteristics and some of the new approaches that I wanted to share with you. First of all, we would like to present a fast and accurate OPF model over a time period. And then the model needs to reduce the complexity of finding solutions under the nonlinear time-varying equations. We also have to theoretically guarantee the system economy and security over the time period at the same time, and to build a coherent schemes between the day-ahead scheduling and the real-time dispatch. And then to achieve these characteristics, these are some of the approaches. Well, the first approach is I proposed a concept called the linear time interval. It's a very simple concept, but it's very fundamental and important concept in the research. So the definition of that is given the time interval, if the real power and the reactive power injections on each bus are linear functions of time. Now we call this interval as a linear time interval. And this defined linear time interval actually exists in the practical power system operations, specifically during the forecasting power output, the time interval, for example, in between the two consecutive time points is a linear time interval, right? And it also varies in a different dispatch level. For example, in the day-ahead scheduling, the linear time interval is 1 hour, while for the real-time dispatch, it depends on the different ISO systems. It could be 5 minutes or it could be 15 minutes. So based on this linear time interval, the second approach is theoretical. It is under the linear time interval, the real part, imaginary part of each node voltages are approximately linear function of time. And if they are approximately linear function of time, then we could just consider or check the security constraints on the two extreme loading conditions that can help us to save a lot of time in terms of doing dynamic optimization. Well, this is the same example, as I said, since we have the approach number 2, to show the approximate linear function of time, then to satisfy the entire system constraints instead of considering all the other time points like dynamic or multi-period optimal power flow model. We can just consider these two extreme loading conditions, which are the two terminal time points in this linear time interval. We also propose a third approach, which is theoretical as well, come from many different propositions and properties. And this is a function that we propose called the time-varying node voltage function. It means the voltage we can calculate from this function has a high accuracy. And the approach number 3 is the maximum voltage error that we calculated from this function can be restricted within 10 to the power -4. So that means we have the high accuracy, we have the high efficiency. We don't have to run the power flow analysis. We can use our function to calculate the voltage directly. So the approach number 2 and number 3, as I mentioned, they are actually achieved by many different propositions and properties. And then we finally proposed the period optimum power flow we call PPOPF, and PPOPF is a whole framework of combining the day-ahead PPOPF and real-time PPOPF. We call everything together as the PPOPF, progressive period optimum power flow. So in this PPOPF model, we consider the medium time point as objective function, the two terminal time points as constraints. What we can theoretically guarantee is as long as the constraints on the two terminal time points are satisfied, then the constraints on any other time points can be also satisfied. And again, the approach number 1, 2, 3 are here to fundamentally and theoretically to just support the approach number 4, which is a very simple model, but it has a lot of background theoretical analysis to support that. And I don't want to share all of those propositions and property because I don't want to make you sleepy, and especially if you're having lunch right now. So let's just directly jump into some of the case studies. This is how I think, right? As an engineer, we always wanted to run some of the case studies to evaluate, to see whether those theoretical analysis from those approaches really work. And here again, we're using this 118 buses to just being provided by the Met Power. I have added some of the other different variable energy resources. And then in this system, we have 20 wind, 10 different solar generators. The penetration of them together in the system is 30%. The total time period is considered as 24 hours. So the reason we designed this 24 hours because later we have to run the PPOPF simulations on day-ahead scheduling, so the 24 hours to match with that. We then use 25 different discrete time points to partition the time period into 24 different linear time intervals. So each linear time interval is 1 hour. And similarly, each of the linear time interval can be further partitioned with 11 equidistant time points. Well, this is a figure I just wanted to quickly show you that we are using a very heavy and random loading conditions, right? Here you can see for the loading variations for the 24 hours, extreme loading conditions are very heavy. And it's about 6 per unit from the highest, between the highest and the lowest. The maximum power differences are even over 1 per unit on 1 hour. Well, just wanted to share with you in the steady state of the power system operations, no, you wouldn't see something like this. And the way I tried to design this is just really to make sure and test whether those approaches would still validate and work under the worst scenario. And speaking of that, the first thing we did is to evaluate the approach number 3. Just to recall, under the linear time interval, we have this proposed function that can guarantee the maximum node voltage error to be restricted within 10 to the power of -4. So to validate this theoretical analysis, I'm just curious to see under each different linear time interval, what is the maximum voltage error in the system? So before showing that, these are some of the steps under the simulation. First of all, under each different linear time interval, we ran the power flow on all of these discrete time points by using Met Power to get the voltage values in the system. And then we consider these voltages are the actual voltage values because we see Met Power as a references, right? For example, we ran Met Power on all the time points of the first linear time interval. Now we have the corresponding voltages from real part and the imaginary part on all of these 118 buses at each different time points. And similarly, we use our combined node voltage function to calculate the voltages on all of these time points. And so now we have one set of the values from Met Power, one set of the values from the combined node voltage function, and then according to the value differences between the Met Power and combined node voltage function, we get this voltage errors on all of these 118 buses on all these time points. So in this 118 bus, the number of the voltage errors for each linear time interval is 2596. And then we pick up the largest voltage error among all of these errors, and then we record the values down here as a maximum. So we repeat the same steps for all of the other 24 linear time intervals, and then we achieve 24 maximum voltage errors under 24 linear time intervals. Well, this is a figure to show you. We then record the 24 maximum voltage errors in the figure. So each of the points represent the maximum voltage error under each linear time interval. So from the figure, we can see that the minimum of the maximum voltage error happens on the 15th linear time interval, which is 1.4 to the power of -5. And then the maximum of the maximum voltage errors of the entire 24 linear time intervals happens on the 12th linear time interval, which is 8.4 to the power of -4. And this demonstrates that even in such a bad scenario, our approach number 3 could guarantee that our function can guarantee the maximum voltage error has to be restricted and will be restricted within 10 to the power -4. And speaking of that, to further numerically demonstrate the approach number 2, 3, right, we just randomly select we just randomly select the 21st linear time interval at the further detailed analysis. And here you see that the figures are the first 4 different buses with the largest load variations on the real power P and react power Q. And now we're interested to see what about the approach number 2. We just demonstrated the approach number 3. And the approach number 2, under the 21st linear time interval, just to recall, our approach number 2 is under a linear time interval, each node voltage factor is approximately linear function of time. So the first thing we do is to use map power to run the power flow on all of these time points, and then we record the voltage values. And then the next step is to use combined node voltage function to calculate these different voltages at any time in between the 2 consecutive discrete time points. And then we then combine these values of the 2 steps in the simulation results. Well, the results are very interesting. The results shown here is the circle mark, actually, they are the actual values we get by running the map power. And then all of these lines in between the 2 consecutive time points are the computational values calculated from the combined node voltage function. And these 4 different buses here are the buses with the first 4 maximum voltage errors under this 21st linear time interval. Well, if I don't share with you that the lines in between the 2 points and these circle markers, they're actually calculated from 2 different approaches, is really hard to tell because it just looks like a straight line. But at some of the places, you can see this is like an approximate linear function of time. And this is to validate our approach number 2, right? And speaking of that, since the errors are so small, it's really hard to tell. Let's just see, under this linear time interval, how does it work? What about the voltage errors? And then this voltage error, again, from y-axis, real part and imaginary part, you can see they're all within 10 to the power -5. Further demonstrate the approach number 3. Another very interesting and important observation I wanted to share with you is the median time point, beginning time point, and ending time point, they have the smallest voltage errors. It's just very close to 0, considering about the order of the y-axis over here. And this is a very important observation because it's going to be very helpful for us to later on select the specified time points for the PPOPF. And speaking of that, right, we were talking about the PPOPF, we were talking about all of these different approaches. And again, those approaches are here to theoretically support in developing the PPOPF model. And the PPOPF model is over here. We consider medium time point as objective function. We consider 2 terminal time points as constraints. Well, there's 3 different reasons. The first reason for a medium time point is because it has a minimum interval power imbalance. So under a linear time interval, the power differences between a specified and non-specified time point, we call that as the interval power imbalance. So for traditional optimal power flow, since the objective function is focused on the beginning time point, and then under this time interval, the maximum interval imbalance is between the point A and point B. Well, if we have objective function is focused on the medium time point, then the maximum interval imbalance will be half of the traditional OPF and will be the smallest. So that is the first reason. The second reason we're choosing this medium time point is because, the type of the objective function can be either cost or profit. And since the energy can be directly price labeled and traded, the objective function can be directly related to the energy. So the medium time point here has the energy integral property. And of course, the third reason is because coming from our observation 3, medium time point has the most accurate results in terms of the voltages. And similarly, there are 2 reasons to choose the 2 terminal time points as constraints. The first one, just recall, because we have the approach number 2, the voltage has approximately linear function of time given the different time intervals. So the voltage has monotonic property. Even if some of the buses has monotonic increasing property, some of the buses has monotonic decreasing property, it does not matter. The voltages in between the 2 consecutive discrete time points, they hold this monotonic property. So that is our approach number 2, which means if your voltage constraints are satisfied, your voltage can be satisfied on any other time points in between this interval. The second reason coming back is still related to the third observation, which is our beginning time point, ending time point for both real part and measured part of the voltages. They are the most accurate. Right? I hope this gives you an idea that why I wanted to spend a lot of time to share with you about these approaches theoretically, just to show you that even if PPOPF looks so simple, it is supported by extensive theoretical analysis behind of it. And that answers our question from earlier of how do we select these specified time points to better represent the time period. Well, this is some of the information I'll quickly show you. We have to do the simulations on a large scale practical European system. You can find the system on the Met Power. It's public, it's an open case. And you could also find, these are the different test conditions that I was running for the simulations. Well, in this study, what I did is we first ran the day-ahead scheduling to compare both traditional OPF and PPOPF. And then in the day-ahead traditional OPF, we first of all, we ran this optimal power flow on the first beginning time point. And then these are the voltage constraints that we have to satisfy for the day-ahead traditional OPF. And now we need to apply the optimal decisions to any other time points of this first linear time interval to check and see if there's any other voltage constraints violations on other time points. And these are the voltage results from the other time points. We apply these voltage values into the voltage constraints that should be satisfied and see if there's any constraint violations. If there is, what is the constraint violation amount and what is the constraint violation numbers for the voltage? We similarly also do this on the thermal limits. Well, this is the figure that you can see that for both thermal limits, voltage constraints, they both have a lot of constraint violations on all of these 24 linear time intervals for the traditional OPF. Right? And then now we're just curious to see what about day ahead POPF model. So the next step is we check all of these voltage constraints of the day ahead POPF. So these are the constraints that we have to satisfy. And the constraints are focused on the beginning time point and the ending time point. And then the next is to check about voltage constraint violations on this model. And similarly, we apply these voltage values from the other time points into the voltage constraints to record the total violation numbers and amount for both voltage and thermal limits. And none of them have any of the violations. So the day ahead POPF has no constraint violations in all of the 24 linear time interval. And this also validated our theoretical analysis. Well, at the same time, of course, it's good to know that our model is secure in terms of no constraint violations, but we also don't want our model to be too conservative, right? We want to make sure that our model in terms of the objective function is also good. So this is to compare the objective function in terms of minimizing the generation cost for both models. And here you can see that the objective function value coming from both POPF is actually very close to the traditional optimal power flow. And even in some of the cases, generation cost is even smaller than TOPF. And for example, on the first linear time interval, this is because the total power variations in this interval is decreasing since the TOPF is focused on the beginning time point, POPF is focused on the medium time point. So the value is relatively smaller compared to the traditional value. Well, this is the real-time dispatch model comparison between the TOPF and POPF. And again, you can see that the progressive period optimum power flow model has no constraint violations as well for both voltage and the thermal limits. And just wanted to highlight that this is a project further, when I was hired by the University of Connecticut, this was further funded by the Eversource, focused on how to do the PPOPF in a distribution system. So really thanks to Eversource for continue sponsoring our research. Well, we were talking about this PPOPF that can be used for grid reliability, right? So now I'm just curious to see whether PPOPF can be applied to other practical applications, such as the grid resilience tools. And this is the background that I wanted to share with you. Is being funded by Eversource as successfully completed in the grid resilience. Here, we're really targeting we're helping the Eversource to see if there's any other way to make the grid resilient, but at the same time to help them identify the critical grid components based on the different type of the event's behavior. And since we're making the grid to be resilient, sometimes it can be also costive. How do we use optimization framework to kind of find a trade-off between this resilient and to make it also cost effective? Right. So with that being said, these are just some of, I'm not going too much of the details, but I wanted to show you, these are some of the primary goals and some of the objectives we have already completed. And one of the things I wanted to highlight is this mesh view grid mapping tool that right now has been utilized in many other different applications. So what is mesh view grid mapping? Well, mesh view grid mapping is the power system you can see is divided into a certain number of the cells. And each of the grid components is located on one cell. It could be a transformer, generator, energy storage, EV, distributed generators, or power lines, right, and many other components. So in the case that if an event has happened, the affected system components can be easily identified from the tool, and the tool can quickly identify what is the exact event locations and what is the boundaries of the events and the regions where the components will not be affected. So we're using multiple layers, including the metrology, the power grid, the topology, and geographical informations to multiple layer these to come up with this tool. And this is another information I want to share with you. This is just an example of a distribution system with a radio structure that you can see here, or maybe with a weekly mesh structure with different switches for optimal network reconfiguration to find out what is the optimal routes if there's any of the events happening. But wanting to show you that the different events have the different affected areas. And this can really help the utilities to go set their crew to dispatch or optimally fix these different areas in a very cost-effective way and in a timely manner. And here, I just wanted to quickly share with you, these are some of the different flow charts, and you can find all of these figures on a published journal. And that we are developing the multi-objective function optimization framework by using the PPOPF, and that is how the PPOPF jumped in over here. Here in this figure, you can see the different type of the events parameters or critical scenario parameters in order to assist us in developing this tool to analyze the events and to help us to develop the risk mitigation plans. Well, this is just some of the examples of the simulation where we also developed some of the quantitative resilience metrics to show that together with PPOP and vulnerability assessment, we can really help with the power grid for the different areas to identify how that can really react into the different type of the events. And this can really help with the long-term resilience planning at the same time. Well, this is, as I said, this is being funded by Eversource, and I wanted to share that my goal is not only just to be using this tool in the northeastern region. My goal is to make sure this is going to be flexibly used in our nation to really help our nation's electric grid in terms of the resilience attacking against with the different type of the events. Okay. And then we talked about the resilience from the technology perspective. And then now I also want to talk about the policy, right? We also have the market related applications. And this is another project that we have just successfully completed with ISO New England. And we're looking at what about the transmission distribution system coordination. And another interesting part is we're helping ISO New England in building a coordination platform to identify what are the critical parameters that can be exchanged in between the two levels. And another thing is ISO New England, for example, it can get the baiting curve from DERA, DERA, aggregated DERs. And we're trying to see if there's a way for us to submit in terms of the baiting curve for individual DERs, and how does that help the ISO or transmission system operators in terms of generation cost, congestion management, in terms of the load shedding. And some of the results can be is actually really good. You will very soon see these figures being published on a journal. That is another good news. And in addition to that, PPOPF can be even applied more, not only the power system applications. And this is a project that we are very lucky to get funded by the Department of Energy, working with Pointeria. And this is a $2 million project. It was funded last year. And the original idea of coming from this is I always tell this story. When I was driving to Yukon the first time when I was hired, because I was hired virtually during COVID. So when I was driving the first time, I see there are many of the trees, and a lot of the trees are sticking outside of the distribution lines. So I was thinking if there's a way for us to be able to really use vegetation management to integrate together with the power system to help the power grid in terms of making it more resilient. And then that is how we got this project. And speaking of that, these are just wanting to share with you some of the public information you can also find online. This is a weather station in the Massachusetts. We're getting a lot of the data. And then this is funded by the DOE. We're using the different LiDAR data scanning to scan all the circuits. And then we're using the different machine learning technologies and then to combine this vegetation management together with PPOPF to improve the grid resilience. Here are just some of the very fancy figures to show you where we characterize what is a critical wind speed, what is a critical wind angle that could really affect the different areas of the trees in terms of the trees related or being very close to the circuits. Okay. And again, these are some of the other figures to share with you. You can see these publications online already, so feel free to check all of those information. But these figures is to show you some of the interesting results. We can see that the critical wind speed for the breakage is even higher than that for the uprooting. And this means that the trees tend to uproot more frequently than they break. And this aligns with the historical outage data. And there's some of the other interesting results. You can find more on the papers. Well, this is another thing I want to share with you. If you see, this is kind of familiar, right? This is the mesh view grid mapping that we have been using previously on the Eversource funded project, and now it's being used on doing the vegetation management to identify the risky tree area based on the different risky factors. And then these are some of the simulation analysis that we're helping the utilities to develop a cost-benefit analysis too. For example, if the utilities has a larger investment plans for the next few years, we could help them to identify the critical areas to do the underground lines. If they don't have if they have a relatively smaller investment plan, then we could help them to identify the critical areas to trim down the trees. And again, these are the quantified risky areas that we have identified. And this is just a very simple high-level flow chart to share with you. And then this is how the PPOPF is being applied into developing the cost-benefit analysis tools. And speaking of that, coming back to the same figure. So we know from the different technology development, technology transition, we have the market policy, and they're all coordinated together from different methods, different tools, different applications to maintain the grid reliability through optimal dispatch. And now excited to share with you about CSU Energy Institute. Well, as I mentioned earlier, this is our this is something funny I wanted to say. I came to CSU to visit in July of this year, so that was before my hair. And when I came here, I already see our amazing team set up the demonstration room, and this is just me taking a picture in July. And then this is one of the demonstration room that we're helping to design for OPAL-RT. And this is just a fancy display figure to show you it's not the real one, but we have specific space for the hardware in the loop test bed for OPAL-RT. We have the multiple different simulators and just very excited to show you. Well, this is right now being constructed, expected to be finished in January of 2026. How does this look like? Well, you have to come and visit us. There's so many amazing opportunities and amazing initiatives that are happening right now. And again, this is just the beginning. Just let me know. Come visit and see what is next. We have a lot of amazing initiatives and a lot of things to share coming next about the opportunities and collaborations with our utility partners, with our providers, and with our state government. And then this is Also, another important thing that I want to share, as some of the examples of the equipment or facilities we have, we are also purchasing other multiple different simulators from OPAL-RT. In addition to these, we also have HPC that can really support our computational resources. Okay, so I was talking about the GMI, right? GMI is coming from the Energy Institute. And speaking of the Energy Institute, this is a figure, how it really looks like. It's really beautiful. And here you can see this is our Regional Energy Institute building that was being built in 1936. Right now in this building, we have this 3.5 megawatt of the gas turbine, and we're the only universities in the US that has this full size of the gas turbine and now is running as a practical test bed. Not only that, in the same building, we are one of the very first university-based 5 megawatt of the microgrid test bed that is originally founded by Denmark, that is also right now running, that we can use a perfect test bed system in between the two. Well, there are some of the other significant milestones for our amazing Energy Institute, and including some of the big projects we just recently received, $325 million from DOE on the Matthew emission and the resilience. We also received an SF engine award that is coming by cooperating together with Innosphere is $160 million. It was funded in 2024. And as I said, this is a figure you see from here. That is our current powerhouse that has 100,000 square feet. We are right now building another powerhouse, which is 160,000 square feet that will be completed in 2028. So a lot of amazing things will come up very soon in public. We also continue to expand from science solution to scale. So that is our goal for all of these. And again, CSU is located in Fort Collins in Colorado. And Fort Collins is a beautiful city. Fort Collins, I wanted to share with you, in 2024 has been listed as the best city to live in the United States in 2024. And Fort Collins is also famous in terms of being the first city to build the underground distribution line and the underground telecommunications line back in 1960s. And we now already have 100% of the underground distribution lines. And the goal, from my perspective, I really think we are very unique, starting from the city of the Fort Collins, starting from the PRPA, from CSU, Energy Institute Grid Modernization Initiative. We have just one vision to make sure our grid is resilient and reliable by using all the technologies we are working together with our collaborators from across the different perspectives. Well, this is a quick conclusion I wanted to share. The work we're doing is really to advance the United States electric grid by integrating different optimization methods, the real-time simulation, data-driven technologies to build a more reliable, flexible, and resilient future. And these are some of the PPOPF model that I was talking through related to the optimization and also related to the market operation. How do we help the ISOs in terms of coordinating transmission distribution systems? And then in terms of the resilience, how do we help the different utility companies to come up with the risk mitigation plan? How do we come up with a better long-term resilience planning? And then how do we use the different AI technologies to really help with the utilities or the other collaborators to make it as an optimal power system operation? And with that being said, that is me. And you can find the email and my phone number, and this is my website. Just feel free to let me know if you have any questions. Send an email to me. Thank you very much, everyone, for listening.
Thank you, Dr. Zhangzi, for your great presentation. So now we'll take Q&A. Folks can put their Q&A on the chat so we can start asking questions. Or if you want to speak up, let me know. You should be able to also ask questions. While we wait for some questions, maybe I'll start by asking, it's interesting about the DOE Whisper project, what did you learn and find out, in terms of, I'm just curious to see the percentage of tree-induced outages, in the country, what is your reflection on that? What do you see in terms of the percentage? Most of the outages are How much percent of the outages are due to vegetation? Do you have any idea?
Yeah, I could tell in a high level from the Whisper project that we are targeting is mostly for the Northeast region, right? So I could tell from the Northeast part that it really depends on the different wind speed direction. And as we simulate, it depends on how the trees is being laid out and how the trees is being interconnected geographically with the circus. That is how we define the different quantitative tools. And in some of the areas, if the trees are not so much, it's not is not significantly integrated with the circuits that we could target specifically from trimming down the trees. But if there are some of the areas that have the significant for example, in the past, have the significant power outages that based on the historical data, we can identify what are the tools and how do we train down the trees and how do we even fix the areas, how do we do the underground lines to make sure that it is being more resilient. So I would say it really depends on geographical information, how the circuits are correlated together with the different vegetation perspective.
Thank you. Yep, so the questions started to populate. Okay, have you identified conditions where the renewable output changes too quickly for period OPF to maintain the high accuracy?
Yes, so that's a good question, and that's the thing that when I shared earlier, right before jumping into that large scale simulation results that we identified a very heavy loading variations with multiple different wind variations and solar variations just to see that how the OPF could maintain its accuracy in terms of working on such a scenario, a bad scenario. So that definitely have already been identified.
In your example for using your optimization model, you only use voltage constraints. Have you experimented with other a combination of other constraints to see how the violations have reduced, or maybe it has complex? I don't know. Just curious to know what you
Yeah,
found.
Prakash. That's a very good question. We have definitely done that, right? So, for example, related to the when we are working on the PPOPF with the resilience metrics, working on that Eversource being funded project, our optimization also including the different resilience type of the constraints, time varying. And I can say that I'm talking more detailed on the voltage and thermal limits because these are the constraints that are well known as really being hard to satisfy, especially during a time period. But in terms of adding the other constraints, yes, we have done that. It really depends on the different type of the purpose for the optimization that we want to optimize.
I know that more and more efforts are going into co-simulation effort to, you talked about building the hardware and the for OPAL-RT in future, are working towards that, right? And
Yeah.
are there any problems that, these co-simulations couldn't solve, or you need some more additional features that we may need to build into these available state-of-the-art tools? What is your perspectives, and to going forward and actually do you think we have so much of scenario generations? Do you think when we talk about extreme weather, things fall apart so quickly? And do you think it's meaningful to realistically model, the using the co-simulation platform? If so, what are we missing at?
Good question. I would say co-simulation is definitely great. For example, OPAL-RT, right? We have the not only OPAL-RT platform, a that is a very popular simulator that can model the co-simulation of the TND. We also have the Helix from Nreal. Right now it's called NLR that are modeling the co-simulation of the TND. From my perspective, I think I always pursue not only co-simulation, but a co-optimization of the TND, especially with different time intervals and how can we combine these different scenarios? How do we identify all of these critical parameters? If we really want to optimize everything together, it's going to be hard to see what is a primary focus we want to do, right? So I would just to answer your question, Prakash, I would say not only co-simulation, but co-optimization and co-simulation to be working together. That is really something that I see as a future for TND framework.
Any applications of AI for accelerating computational problems in OPF? Where do you see its real application?
Well, we can talk about that for days, right? And I could share some of my perspective, right? So, for example, when you do the OPF, you get a lot of parameters, and parameters usually can come from including the different forecasting, right? And then, of course, you can use AI, machine learning technologies in terms of doing forecasting, downscaling with all of these different parameters, and then as input for OPF to help OPF to quickly jump into a better optimal solution. So that's definitely one thing that I see is critical. And of course, there are many other different AI opportunities to be applied into OPF, especially comes in multiple, again, spatial, temporal constraints with multiple different time intervals. Yeah, there are many different applications for that.
Another question. Can you explain more on what major assumptions the OPF approaches you mentioned should consider or adapt to, especially with higher single-phase DER penetration?
Major assumptions of OPF approaches should consider, especially with higher DR penetration. Well, that's also a good question, right? It depends on what you really wanted to optimize, right? So, for example, right now in the steady state of the OPF, when we're trying to optimize the DER, we consider DER as either a decision variable and can be kind of combine this into part of the OPF framework. And some of the other assumptions can also be like if you wanted to model like a deterministic optimization in term, instead of a dynamic or instead of a dynamic or robust optimization or stochastic optimization, you could consider those different DR's assumptions as just the forecasting values as inputs in your OPF. So there are different assumptions. It really depends on what you're trying to solve or trying to optimize.
Hey, let's see. Yeah. So
But these are all very good questions. Very happy that yeah,
if
with this
folks want
very
to
interactive.
using audio, please feel free to add. I know there are several faculty also listening. I'm not sure if they want to speak up and ask questions. Please do.
Feel free.
So, um, well, one of the things I was talking to we had some workshop a few months back or just last month back, and there's so many parameters out there when you look at optimization or power imbalances, how do we boil down to key fundamental parameters? You have listed 8 in your slides, but when this current administration is focusing on more priority to Genesis project or more AI-driven approach for grid resiliency, and is there any way to boil down to one or two parameters that you would think, from your opinion, would help to really to say something about system instability that's happening or power imbalances, and how would we actually, go from there when you really want to look at such a fine-grained time intervals? Do we have any couple of key parameters that you would think, from your opinion, are more important than others, or just to
Very good question, Prakash. And I can say you mentioned about the resilience. So let me just give you an example about the resilience project. So when we try to target the different type of the stages of the events, we usually have pre-events, during the events, after events. So when we do the optimization, we of course have the different parameters for each different stage, right? So let's say when we're trying to do long-term planning, then optimization, the critical parameters can be anything related to what about the event's duration, the event's kind of the parameters. And if we're talking about, for example, the vegetation related to the resilience, then the critical parameters would be the wind speed, right? It would be all of these, the other different critical parameters that can be integrated into the grid operation. And if we're talking about building a quantitative resilience metrics specific focus, the parameters can be anything related to those metrics, right? And then these are the things, I think is really vary depending on what we are trying to develop. And then in terms of, let's say, if we're not talking about resilience, if we're doing a project for coordination T&D, right? The critical parameters could be what can be really exchanged, for example, from distribution side to the transmission system side and what can be changed, for example, from the point of the coupling perspective, right? What about the DER generation output? What about the other generation output? What about the load variations? So these are all the critical kind of the time points and the related to the parameters that ISO really wants to know. What is a gen point? What is the state estimation points? What is the power flow, parameters? And these can all be the critical information. It really depends on the different projects we're working on. But fundamentally, right, the critical parameters, would be, for example, when we do optimal power flow, it would be all of those very fundamental basic parameters for doing the OPF. And then we're adding into other additional critical parameters based on the different projects we're working on. I hope that
Thank you.
helps.
Yes, thank you, Dr. Zhangzi, for your time. I think we're going to running out of time right now. I think we're going to close the webinar. I appreciate your time for this morning with us, and you
Thank
will
you.
receive a nice plaque from UND. And thank you for being so supportive for the webinar and all the collaborations. So we'll continue to work with your
Thanks very much,
lines.
Prakash. Also for supporting NAPS 2025. Thank you. Okay, bye everyone.